So the half-life, which is represented by t to the 1/2, is the time it takes for half of the reactant to be converted into product. We're going to look at first order and second order overall reactions. Let's look first at the first order overall reactions. There are two equations here that show the relationship between concentration and time. I prefer to use the natural log equation though. A is the concentration at time t, A sub 0 is the initial concentration. We can derive a half-life equation. Don't worry about the derivation, but here's my half-life equation for a first order overall reaction. So we have two equations for first order. Part A of this problem says to find the half-life of N2O5 at this temperature. This is a first order overall reaction. So the half-life is equal to 0.693 over K. So 0.693, we're given K, the constant in the problem, 1.68, 10 to the negative 2 reciprocal seconds. So when we solve this, the half-life for this particular reactant is 41.2 seconds. So every 41.2 seconds, what this means is the concentration of N2O5 goes down by half. So if I start with 1 molar, after 41.2 seconds, it's 0.5 molar. After another 41.2 seconds, it's 0.25 molar, and so forth. Second part of this problem wants me to find how many moles remain after 1 minute. Well, since I'm not using the half-life, my other option here is the relationship between concentration and time. I'm going to use the natural log equation. So it looks like this. I want to know the amount of moles present after 1 minute. So I'm going to solve for the left side here. K is the rate constant, which I was given in the problem, so negative 0.0168 reciprocal seconds. The time here is 1 minute, but since I'm in seconds, I need to cancel those units and make it 60 seconds, plus the natural log of my initial concentration. Well, the initial concentration is 2.5 moles over 5 liters. So when we solve, we get the natural log of N2O5 equal to negative 1.70. Now to get rid of natural log, there's a function on your calculator, e. Just take e raised to negative 1.70. It should be right above the natural log key. So e to the negative 1.70 would give me the concentration, and my concentration is 0.182 molar. But I don't want to know the concentration, I want to know how many moles remain. So I got the molarity. If I multiply molarity times the volume, which is 5 liters, I will get the amount of moles that remain after 1 minute, which is 0.910. So there's my two equations for a first order overall reaction. We're also going to solve reactions that are second order overall, and there's two equations here as well. The relationship between concentration and time is right here, and the half-life equation is right here. Now on the test, you don't have to memorize these equations. However, you do need to know that this is a second order equation here. So I'm going to give you the equations, but you need to know if they are first or second order, respectively. So in this problem here, it's a second order overall reaction in I, and we're given the rate constant at 23 degrees Celsius. The first part says if the initial concentration is 0.086, calculate the concentration after 2 minutes. So the equation that we would use here, since it's second order, is the relationship between concentration and time, which looks like this for a second order reaction. So I want to solve for the concentration after 2 minutes. So I'm solving for the left side. My initial concentration, I'm told, is 0.086 molar. So that goes there under A0. K was given in the problem, 7 times 10 to the 9th 1 over m times s. And since we're in seconds, the 2 minutes, which is the time, make sure that's in seconds so that we cancel out those units. So 1 over concentration of A would be equal to, when we solve this, 8.4 times 10 to the 11th into the minus 1. I need to invert that to get the actual concentration that remains after 2 minutes. So if you invert it, take 1 divided by 8.4 times 10 to the 11th, you get a concentration of 1.2 10 to the negative 12th molar. So we started with 0.086, and after 2 minutes, look what happened to the concentration. There's hardly any left. So that's a very quick half-life. And in fact, part B asks to solve for the half-life for this particular reaction if the initial concentration is 0.6. Well, in order to get half-life for a second order reaction, it's 1 divided by K times A sub 0. K we were given 7 times 10 to the 9th. And the initial concentration, and this part is 0.6 molar. Again, the previous problem, part A, showed that it was a very quick half-life. In fact, when we solve this, we see that the half-life is 2.4 times 10 to the negative 10th seconds. So every fraction of a second, the concentration will decrease by half.